Okay, we're gonna have a story of the day. We're not gonna have a quote of the day. We're gonna have a story of the day. Okay, so I think this is cool. Shihang, you have to pardon me. I already told you this story. We were in some taxi going somewhere or other, but so you already know the story. But I think it's a fun story to share, and it talks about what it's like to do very detailed technical work and what it's like to encounter issues that almost make your heart stop, and then hopefully fight your way through and figure out the answer. So don't worry. Now it's going to get a little scary as we go on here, but at the end, it's all going to be okay. So here we go. Itasca also makes a code called FLAC3D. This is a FLAC3D model. It allows you to model solid continua, and it has pretty much every possible rock constitutive model existing on the face of the Earth. So people who are doing state-of-the-art complicated rock mechanics use the FLAC3D. And it also has the ability to put in these things we call structural elements. And you can see what these are. This is a shell. You can see this is an excavation, a trench. There's a shell structure that maybe someone's walking across it from side to side. There's a beam structure. Up here is a cable bolt in the wall. This is another type of cable bolt. Back here is a geogrid, which is something you can embed inside a material. And this geogrid is in there. It's getting pulled out. This is a liner of a tunnel. It's lining the surface, and this is a pile that's been driven in. That's how it's being displaced. Okay, I'm the guy who did all this stuff. I implemented all these structural elements in FLAC3D, and I did this this is actually using finite element technology, and it's coupled with FLAC3D. So for example, the edge of this shell, you can see it's deforming. That's the deformation contours, vertical deformation. It's loaded by a pressure. You can see it's not deforming on the edges because those things are rigidly the zones. We call these things zones in FLAC3D. And so these things are coupled. And so this is a finite element thing. So I'm the shell guy. So I developed all that ages ago. Some of you may not have been born. I started doing this, and I did that in 1998, the original implementation. And it's slowly been made a little better along the way. And then a big thing that was done by me about 5 years ago was to add the ability for these shells to deform plastically, which means they can yield and things like that, because typical liners might actually start to yield. So we want to be able to do that, and doing plasticity in shell finite elements is freaking complicated. I spent a lot of time. I finally figured it out, and once I figured it out, like everything, it's quite simple. So I was putting in plasticity, big, huge. Took me 2 entire years of effort all the time. That was my main world, of putting in plasticity into these shell elements. So I'm in the middle of doing this, okay? And just so you get an idea, don't look at the picture yet. Look at this as a boundary value problem of a shell. It's a circular shell, and it's simply supported on the side. So I don't know, in the United States, we have these sewer covers, we call them. When you walk around the street, they have these circular plates, these that are maybe like a meter in diameter, and you can open them and go down to do stuff with the sewer. So it's a plate. It's a steel plate. And we're going to just apply a pressure loading to the top, and we're going to look how it deforms. And the cool part here, of course, is this is going to have plasticity. So here we go. And as we're running the model, we're plotting the pressure. We keep slowly incrementing the pressure, and we're plotting here on the x-axis the center deflection of this point going down or going up. I can't remember. And as we're doing, so if this was a linear elastic problem, it would just go like this. Notice that the force displacement, pressure displacement curve is a straight line, right? That's linear, just like the linear parallel bond model, right? If it hasn't started sliding, like in our granular material models and in our bonded models, typically after they break, they have a friction coefficient, right? And once something starts sliding, that means it's no longer elastic. That means if you unload it, it won't go back to where it was before, because energy is dissipated when it slides. In this type of world, we do that in a continuum way, where we have a whole theory called plasticity that lets things basically start to fail. And so what should happen here, since it's being pressure loaded, the highest stress on this sucker is in the center here. And so that would be the region that should begin to fail plastically. And as it fails plastically, because it's bending, you have compression on the top and tension on the bottom. It starts to yield. It reaches the critical point on the outside, top and bottom, but it still has capacity inside. And so, but if you continue to bend it slowly, the yield zone grows till it gets all the way through the whole entire shell structure. And after that, it can't carry anything anymore. And so what you're going to see is as we continue to apply pressure, it's going to become nonlinear. It's going to reach a peak value, and which is the where we basically would call that the collapse load, because that pressure, if I put more pressure on, it can't sustain it, and so it'll plateau at a certain pressure, and it'll just keep displacing. It'll go like this, go horizontal. And you're going to also see colors here, and they're going to show the extent of yielding. And so you're going to see a yield zone start in the middle and go to the edge. And in addition, there's color with that, and the color is going to be how much percentage of yielding has gone through the cross-section. So it's going to start off with a certain amount of yielding that's going to spread, and then it's going to go back here again, and now that's going to be fully yielded. It can't do anything. And so you'll see these color things. So there we go. It's yielding to a certain amount. You can see this is no longer linear because that's not carrying all the load anymore. It's yielding on the outer fiber. The overall result for an applied pressure is it deforms more, so it's not linear. And now that yield zone is growing out, and now it's going to... So now all these guys are not able to carry any more load. And now you can see, oh, wow, it looks like we might be almost at the plateau. And we are at the plateau. Wait, let's just get that. There, you can see, and you can see the deformation, right? So this is just cool stuff because I think it's cool. Plasticity. This is what I did, okay? But to get here, notice this. Now, this is a numerical thing. This has to do with when we do the math, we have to do an integration. And when we do the integration, we have to do it numerically by using something called Gauss points, which I'll show you in a minute. And the bottom line is you can control this. The more Gauss points you have, the better the solution. And that's what that's showing. We're saying as you increase the number of integration points, you see that this collapse load, which is a theoretical thing, is getting approached from above and below. But of course, if you use more, it runs slower. So to implement this, I had to implement this integration. Okay, and I needed to confirm whether or not it was correct. So let's do a quick little go back here a little bit about the theory behind this stuff. It's just like PFC. Everything is, because it's just mechanics. So here we go. Here is a shell structure that's a square, and it's been discretized, in this case, not into particles, but into elements. These are called elements, and this is something called finite element approach, where you take a continuous structure and you perfectly discretize it into different shapes, and then those shapes are perfectly connected along these edges. So the edges are just like contacts in PFC. You could think of this as 4 rigid blocks, and there's a contact model here. And basically, a continuum code is the same exact concept, except this contact model is a bit more sophisticated because we're talking about stresses and strains here. So we start with an element, and what happens? We have these things called nodes, and these guys can move. And basically, as these nodes move, they stretch the element or they compress the element. And so we're constantly taking small steps in time. We load somehow, we take small steps in time, and we keep updating these stretchy forces. And notice this node, this is the amount of force that the node is applying to the element. Like, think of the elements pulling back with that much, given a displacement. Well, this guy also has an answer for that, and this guy and this guy, so you sum everybody up. Remember in PFC, you go to every particle, you sum all the forces up. You go to every particle, you sum all the forces up. You do F equals ma to figure out where it moves. We're going to do the same thing here, but we're going to do it for each node. So watch. Oh, there's our friend, Isaac Newton, comes back again, F equals ma. So this is the same exact thing. This is actually called explicit dynamics, which is what PFC is. And so we sum up all the forces. So at every node, we sum up all the forces, and we can relate the forces then to the change in velocity. And here we go. The new velocity is the old velocity plus F over m delta t. This is the exact same equation that we're doing in PFC, okay? Except we're doing it again for every particle. We're summing up the forces. Notice the particle has a force, total force acting, it has a mass. In here, these nodes have a mass. They accumulate mass from the elements that are connected to them. The elements actually have a mass, but we give part of it to each node. So there's my recipe to update the velocity at the new time step. And if I know the velocity and I multiply it by the time step, I can get the displacement. This is the displacement, how much it moves. And again, we do the same thing with PFC. Now, if we know the displacements, we have to update these forces. And then we're done. If we can update the forces, we can go back to here and we can just keep doing this every time step. And it's the same thing. We have to choose a time step based on stability considerations, same kind of thinking. So check this out here. Now, if it's an elastic system, not plastic, there's a thing in finite elements called a stiffness matrix. And what if you know this, look at this, it's magic because you figured out the displacement increment, which means if you hit it with this magic matrix, you can then update the force. This is the new force, that's the old force. And so what is a stiffness matrix? Basically it's a closed form expression based on, here we go, area, rotational inertia, all kinds of stuff, area, Young's modulus. This is an example. This would be a beam finite element. In our case, we have a shell finite element. We don't got to go into any more detail. The key thing is there's a known analytical solution that lets you build up this sucker here. And this is what I had already done ages ago in FLAC 3D. And so there's a known analytical function for this. So I implemented all that and we could solve all these elastic problems. Cool. But if you do plasticity, you have to do it differently. Again, I'm just trying to get the new force. And it's basically going to be this thing, which is some magic matrix called the B matrix. And this is the stress acting there. And what you have to do is integrate that over the entire volume of the element. Okay. Now, this is where I have to do an integral now. There, okay, and I don't have a closed form solution. So I'm going to have to do some numerical integral. I'll show you that in a minute. And then to check if it all makes sense, if I take my plastic solution with that crazy integral that I implemented, and if I set the strength of the plastic material to be infinite, well, it should now behave like an elastic material. And so the solution it gives, the overall solution for this, if I want to test this system, is I make it infinitely strong and I can run two models, one that uses the stiffness matrix and one that uses this. And they should give me exact same answer. So it's cool because I have a way of determining if I implemented things correctly. Okay. Let me stop for a second. Does this kind of make sense so far?
Yes.
Yes. Okay. Now, let's look at what I did here. We're going to get to the scary part soon. This is what I said before. Okay, so I have to implement this integral and I should get the exact same results if I use this or if I use this. Okay, so how do I do this? And we say we call this evaluate the integral numerically. What does that mean? It means we approximate it. We approximate it with this, in this case, a thing called Gauss quadrature. Look, it's a simple idea. Here's a function. I don't know what the hell the function is. It looks like this. Function of x. And if I want to get the area under the curve, because that's the integral right there, I want the integral of f of x dx. Well, what I can do is I can find certain places where I sample the function, that's the dot, And then if I sample it here in the middle, and if I multiply it by this width, that gives me this area. And then if I sample it here and multiply it by that width, it gives me that area. And the sum of these rectangles is going to approximate the actual integral, the area. And you can see also, if the more of these sample points we have, the closer it will be to the real solution. And so what that means is you end up having these points, the xi, where do you evaluate it? And these are we call these weights. And the last thing is we do a Gauss quadrature, because Gauss was a really smart guy, and he figured out that if we do this and use the specially selected set of points and weights, we will perfectly integrate a polynomial of a certain degree. And so that means if you do the Gauss point solution, and if you know that this is like a polynomial, you'll get the exact answer. This is an approximate answer right here, because these things don't always exactly add up. Okay, Gauss quadrature. And now we have to integrate. So here's a shell element, triangle. Here's the mid surface, we call it. And a shell just simply means a 2D surface that has a thickness. And so here's a thickness, T over 2, T over 2. And so we have to integrate. See these little boxes? These are our integration points. There's a pile of them on each edge. And so the more of these we use, the better the solution will be. So cool, I figured all this out, and I'm like, this is awesome. Okay, and I want to have the user be able to choose how many integration points to use. You know, it depends how important it is if you get the answer exactly right or just close enough, and so you can decide yourself which one, how finely discretized it should be. So cool. So it said I'm going to go from 2 to 12. I'm going to let people do it with 2 or 3 or 4. And everyone you use is going to have a different set of these points and weights, right? Here's using 3 points, and there's a certain value, location, and a certain weight. And if you used 4 points, there'd be different locations and different weights. So what this means is I had to find all of these frickin' solutions to the Gauss quadrature points and weights. So check this out. This is so cool. Look, I go back to the library in the deep recesses of the library, and these mathematicians figured this out, 1942. I love it. It's such an old paper. There's no PDF of this sucker, man. And so here it is. They did all these computations by hand. 1942. Oh my God, there weren't computers. They really did this all by hand. And here's what they got. Here's, for example, if you have 5 integration points, here's the weights and the locations, and these are symmetric. That's why there's only 3, but it's 5 points. And so here we go. Here's my magic numbers, and they gave these out to 12 significant figures. And so so I got all this table. So then I have to go and write C++ code to put these in. So I had to write this freaking crazy code that has case 2, case 3, case 4, and then these numbers here have to be to 12 digits exactly what these numbers are. And if that's all done properly, and if Gauss's solution is right, which everyone agrees this Gauss thing is correct, and if these guys did this right, that means this table should be right, and for God's sake, it's a journal paper, it's got to be right. So here we go. It's just a question of me being careful enough that I get every single one of these numbers exactly right. And if these are not exactly right, the answer will be slightly wrong. Okay, so I did all this. So then I need something to compare this to. So we go here. This is an analytical solution, simply supported plate with a pressure load. And we know the maximum deflection. And we know this to much more, we have an analytical expression. So we have it to all digits, right? So I run this problem, right? And I run it with a stiffness matrix solution, and I get an answer for the deflection, 2.6457938 millimeters. And I run it for both cases, my plastic thing, and I get the same answer. Awesome. What if I have 3? I get the same answer. Awesome. I'm just sitting here like, oh my God. Okay, let's see if this is right. Get the next one. Run the next one. Oh, this is awesome. This is all going to work, right? Go, no. Last one. don't get the right answer. It's super close. It's only off in the 10th digit, right? Which means, you know, the answer was 5 point blah, 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 blah. Well, that 10th blah was not the same. And I assume that my previous solution was correct. That stiffness matrix thing. It's been in the code for 16 years. So now the question, I'm like, oh my God. Okay, well, I probably just didn't write these numbers right. Okay, so I go in and I look at all those numbers, and yeah, here we go. So I look at all those numbers, and I go and I look in my code, and they're all exactly the same. They're exactly what's in here, and I'm not getting the right answer. And it's like, what? Oh my God, what could possibly? So what would you do at this point? I need an answer from someone. What would you do? This is you. You've spent 2 frickin' years to get to this point of the final implementation, and something is wrong. Any ideas?
Well, maybe find why makes it wrong would be also an interesting thing.
I'm sorry, say again.
Well, I guess to find why or what makes it wrong would also be a thing that we are interested in. So just find why it goes wrong.
Yes, that's what I'm trying to figure out. So what could be, and I coded up exactly the same thing as is in this paper. So what's a possibility here? Possibility here is that this paper doesn't have the right answer. Our assumption always is, oh, it's a journal paper, it's all perfect. Well, people make mistakes. And so I found a completely different source, a theoretical source with the solution to all these magic numbers here. And oh my God, every single thing was right in this giant set of numbers except those babies right there. It is, paper says 333, it's supposed to be 233. So only these digits are different. So I went and I put these in and I ran it. So now it's like, oh my God, now holy crap, now it has to be right. Otherwise there's something I totally don't understand. So I take a deep breath to see this is the scary part, right? Because I'm not sure what I would do if it didn't work. So I run this thing and like, boom, I get like exactly the same answer with both things. And so I'm a happy person. So yeah, that's what it was. Check, hurrah. So I just kind of share this because I think it's a fun story. I think it's actually a very fun story, and there's almost no one on earth who can understand this story. I think you guys pretty much can. And if you do a little more of this, this is an understandable thing. And it has to do with a whole bunch of, I think it raises a whole bunch of interesting points. It raises like how careful you have to be when you do this type of work. And it's the same thing for you guys, right? When you're doing this kind of PhD level work, you got to basically get things oftentimes really correct. And even journal papers are sometimes wrong. And it's not that they did anything wrong here. This business is clearly like a typo. They had to type in like 200 different giant 10-digit numbers. And, it's not really surprising that especially then someone screwed up three digits in there. And the other thing, this is another big takeaway. I actually had the ability here to compare with something. I was able to compare with that stiffness matrix solution that I had implemented. And so otherwise, there's no way I would have known this. This would be an existing code out there, commercial code. People use it, and it's wrong. And that's also why every time you guys do research and you try to develop something new, you always do everything you possibly can to find some other solution, and and you then will compare what you get with that other solution. Usually the other solution is like a simplified version of what you did. And we know that that's, and you got to make sure that's the same. And then your research has somehow extended that. And so this is kind of a basic thing that we're always doing, right? We're trying to come up with new stuff, but we always need to make sure it's matching whatever we possibly know as we go forward. So, okay, thanks for listening to my story. Hurrah. All right, PFC around the world. That's just a half kilometer from my office. I think that's kind of cool. Here we go. 2 more lectures. This is what we're going to talk about. We've started talking about the microstructural physics and how we can build different models that represent the different microstructural physics in different ways. And we're going to finish that. And then we're going to talk about how in the heck can we build a bonded particle model and choose all of those different properties so that we can match the behavior of a particular kind of rock. And unfortunately, we don't have a theoretical, and there is no theoretical solution for how an actual rock behaves in detail. All models, all theories, continuum theory as well, they're all approximations, better or worse. And so what we then do, of course, is compare it to experiments. But usually, in almost all cases, they're doing complicated things with the rock, and it's failing in things, and you can't measure that stuff super precisely in experiments. So we're always ending up having to do the best we can, doing a calibration thing. And so what we're going to be doing here is we're going to be constructing a microstructure and choosing its properties in an iterative fashion so that we can match what we believe are relevant results of relevant tests. Okay, like what tests are the ones from a rock? Like AYAT has been doing some granular stuff, and the test she chose was an odometer test. What happens when you squeeze stuff in a rigid cell, and what's the stress strain curve that you get from that, right? That's something you can measure in the lab, and she believed that was a reasonable thing, and if her model could match that, then we say whew, like I did on the, when we say hurrah, actually, and we think that that's a reasonable model and we can move forward with it, right? So that's what we're going to talk about. And then the last lecture will be next week. And now hold on, I got to go. And remember, I'm developing all these lectures as I go here on the fly, so you have to give me a break here. Everything is not perfectly smooth. So this is where we got at the end of last week. And what we talked about, I just wanted just the highlights so we continue on here. Sorry, caveat, back up a second. AYAT had asked me if there are any rock mechanics type books that could be useful. So you can look at all this yourself, but these are 3 quite good books. And this one in particular is fantastic because it talks all about microstructural physics from a laboratory experimental perspective. And that's, of course, what we're trying to make our models do. And then these are different things related to bonded particle modeling. This is this material modeling support package that we're going to use to build materials. And it's on our website. You can download it. You can use it. We'll be going through that. This is the latest work and we'll talk about this next week. And there's also a package so that researchers, this guy here, that researchers can use this to build these materials and do tests on them, lab tests. And then there's also this whole, ages ago, I taught a course at University of Toronto, and you have all this stuff, and they're in here as part of that course. I've got like a history of BPM development and all kinds of papers. And so it's this thing here, and here it talks about kind of the history. This is the Kundal paper, this is the bonded particle modeling paper, and then blah, blah, blah. Things have been slowly added to that as we go forward, and there's all sorts of stuff in there. So that's, if you're really going to be doing this stuff, you might find this useful to at least review this stuff. And we talked about the rock, complicated thing, crystals, amorphous particles, cement. So we're going to model it as cemented grains. And when we load that thing, it's going to start to break. And we actually want to often look at how it breaks and how it evolves, how the behavior evolves as it breaks, right? This is the key thing here. In rock, when you squeeze it, it causes tension. And rock at the micro level fails in tension. It pretty much never fails at the micro level in shear. It's crazy, as Shihong would say. It's crazy. It really only fails in tension. I spent like 3 summers ago looking at every freaking paper I could find in the published literature to try to find little pictures of 2 little tiny grains breaking in shear. And they're almost non-existent. The shear response is a macro response, like an entire specimen begins to fail in shear. But at the local level, you squeeze rock, because of these mechanisms, this heterogeneity, you get tension, and it's the tension that makes it start to break, okay? So any model that's microstructural needs to have mechanisms to produce this stuff. And here's an example of, in a bonded particle model, you can see these are the mechanisms. It just naturally, when you squeeze it, it causes tension in those springs. And then we talked more about that stuff, about the different behaviors as things fail for granular materials. Oh, and the other set the stage here. In order to try to make a distinction, because behaviors are very different, and you could, at a high level, you could map all rocks and you could say they're either compact or they're porous. And this is all from that book. This is the experimental stuff, and this is what they do, because they're trying to describe everything about rock and what we know about it experimentally. So they introduce this high level thing, because rock, the way it behaves is because of what's happening at that pore space level. So we talk about compact and porous. So we're going to use that same lens when we talk about how we can build bonded particle models. And there's going to be different behavior for compact. The compact rock, when you load it, is going to, that's granular. This is the compact. You're going to get these little micro cracks that form between the grains. And when you squeeze it vertically, most of those cracks are parallel to the vertical direction initially. But if you have a porous rock, it's much more complicated. But if it's reasonably well cemented, it's still pretty much the same thing. You get these cracks that are aligned parallel to sigma 1. But because there's all this pore space, you also have initial porosity, you have pore collapse, all kinds of things if you go further along. You may also have grain breakage. And so we're arguing that if you build a bonded particle model in an intelligent way, it actually allows you to explore the fundamental behavior of how rock-like materials behave. That bottom one, how does the microstructure affect the behavior of the rock? And we have an amazingly rich microstructure that we can build. We can build a huge number of different microstructures with this approach, okay? And only a very small part of those microstructures have really been explored, which means there's a whole bunch of interesting things that are still to be done to better employ this methodology. That's why guys like you can keep on doing research and both using this and perhaps moving it forward to perhaps extend in a clever way the kind of microstructures that we need to have. Okay, now, and the one thing, I don't have my phone because I forgot to bring it. And so I normally have my phone so I know the time. And so I need to be able to know the time so when we can take a break. So if you guys could tell me, like, what time is it now?
It's like 9:43 in China, so maybe it's
8:43
in America.
Yeah.
Hey, what time is it?
It's 7 for me, so 8 for you. 8:40, 8:43.
8:43. Okay, cool, cool. We'll stop. We'll take a break at like, 10, 9:45. Okay. So let's get going here. This is just a second. Yes. Okay. We're going to talk about this curve. Basically, almost everything about rock mechanics is encompassed in this curve. This is experimental results, and this is how we interpret the damage process in rock. Okay. We call these characteristic stresses. And this is what happens when you load rock in compression. There's different behavior if you load it in tension. The tension behavior in general is pretty simple. You pull something and it rips apart with a fracture down the middle, at least at a first level. But in compression, it's much more complicated. And in almost all cases, things we build rock in, we're concerned with what's going on around those excavations. It's always loaded in compression. So this is really fundamental. Okay, so what do we have here? This is a uniaxial compressive strength test. I'm assuming you know all about this. This is take a cylinder of rock, and they're usually really small. They're usually like 50 millimeter diameter, and often they're 100 millimeter height. And by the way, the reason you do that is because when you're squeezing with those platens, there's always some friction that the platens there's friction at the interface between the platens and the top of the cylinder. So when you squeeze it, the cylinder wants to bulge out, but if there's friction on the top and bottom, it's like having a little hoop there restraining it. And so that makes things really complicated. The idea of the test is to have a pure uniaxial state. So the stress tensor everywhere is just, there's just one stress in there, no shear stress. It's just axial. And so that's something to be thought of. And so to minimize that effect experimentally, you try to move the platens make them farther away. Like if you had a giant long thing, no matter what's happening, if it's 10 times longer than the diameter, you don't really care about what's happening far away at the platens. It doesn't really matter. But as you make this thing smaller, if the diameter is the same as the height, then that platen effect is going to have a big effect. And your interpretation of the results is assuming you have uniaxial stress, because that's the interpretation that the experimentalists have in making sense of that, because they're using continuum theory. So they're thinking about everything in terms of stress and strain. And so that's why in rock mechanics, you always use aspect ratios of, two or more, almost always. So this is a test that was done in 1993 on a rock called Lactabane granite, which is taken from a quarry about 6 hours north of me, just across the Minnesota border, near Winnipeg in Canada, and it's near a city called Lactabane. And that's pretty much how we name rock. We do it in this crude way, right? Oh, Castlegate sandstone, because it's from this Castlegate area, right? Lactabane granite, right? Da-da-da-da-da. So this is a granite. We'll show you pictures of it later. This is considered to be like typical granite, okay? And so this then is a UCS test. Take that small cylinder, put it between two steel platens, put special crazy Teflon stuff that you spray on there to try to get almost zero friction. And you slowly move the platens together. Typically the bottom platen doesn't move and the top one is slowly pushed down. And as you push down, you're measuring the force pushing back. You divide that force by the cross-sectional area of the specimen and you say, that's my axial stress. That's what you're measuring. And you're applying axial strain. You're applying displacement from the top. And you're doing this very, very slowly. Typical test like this might take 30 minutes because you want to have it be quasi-static, meaning we don't want to worry about the effects of rapid loading. If you load something really fast, that means you're accelerating the material, and that means the force pushing back on you is higher than it would be if you loaded it slowly. I like to think of if I had a bathtub and it was filled, think of a bathtub filled with water, And if you put your hand in there vertically and you slowly move your hand, there's a very small force you feel the water resisting. If you move your hand really fast, you feel a bigger force. So if you were measuring that force, you would say, oh, wow, the force I feel is related to the velocity. And the same exact thing happens for a solid material like rock. So you need to load it slow enough that those effects aren't there anymore, meaning that if you loaded it even slower, you still get the same stress strain curve. This is what we do in the laboratory. It's really important. Experimentally, it's also has to be properly done when you do this numerically, which means what we're going to do to calibrate is we're going to do synthetic tests. We're going to model the same test, and we're going to apply Platon velocity, and we need to make sure that that's slow enough that we get the same answer each time. And so that's a very important thing. So this is a quasi-static test, and what do they measure? Let's talk about what you measure here. The simple thing you measure is axial stress against axial strain. So this is the curve you get, okay? And I'm only drawing it out to this point. We'll talk about this in a minute, but what else do you measure? You also measure lateral strain. And so if I were to draw a cylinder here, I squeeze it vertically and it bulges out. So the Poisson effect. And so that's the lateral strain, the bulging out. This is compressive, axial compression. This is bulging out. That's why they're on opposite sides of the vertical line. And this initial slope here is the Poisson ratio. Okay. So that's what they measure. That's all they measure. Okay. That's all they typically measure directly in the test. They might wrap a chain around the diameter of the cylinder, and they can measure the elongation of that chain. And that elongation of that chain can be related to the lateral expansion of the cylinder. Or they put, well, there's all kinds of different experimental ways that this is measured. Now, from that data, you can compute what we call the volumetric strain, change in volume over volume. The volumetric strain we can show is related, it's essentially the sum of the strain in 1, strain in 2, and strain in 3, X, Y, Z. And for this case, those things are just axial and then 2 bulging out in the cylinder, and the bulging out strains are the same. So you can work out an expression for an elastic body. What is the volumetric strain? But we don't need to work out the expression. We know theoretically how to measure volumetric strain, and we can get it if we know the lateral strain and the axial strain. So then this curve here is what you get. Based on these two curves that you're measuring, you get this curve. And what is this? This is volumetric strain. So what this means is this is contraction. Okay. And this is when you load an elastic body, when you compress it, and you compress a cylinder, what it actually does is the volume gets less when it's elastic. Think about it. We push a cylinder down by delta, and it bulges out by less than that, because that's the Poisson ratio business. Poisson ratio for rock is like 0.2, 0.3, which means you push it down 1 unit and it bulges out 0.2 units. And that means that it actually, when you work out the volume change, it actually is contracting. Okay. So if it was elastic all the time, this curve would just keep going up like this. It has this slope. Okay. So that's what we're measuring. Now we're going to have to interpret that. And the way that rock mechanics people interpret it is by looking at the behavior of the system at different points during the test. And they're going to call these points, they're going to denote them as a characteristic stress. Okay. And here's how they get these things. Let's just start with the beginning here. So you start squeezing the rock specimen. And notice it starts stiffening like this. Stiffening means the slope gets bigger. Then the slope stays straight. Now, have we seen this before? in the stuff we've done for granular systems. AOD, what do we see in the granular systems?
Not very sure under experiments.
So do you remember for the odometer test, when we start to squeeze them, they start to stiffen just like this, and then they become linear. The curve
Yes.
bends upward at the beginning. Okay, and that's what you measured in the lab, and that's also what our PFC models were showing us.
Yes.
And so the same thing is happening in the granite, but for a different reason. And granular material has these grains that are frictionally sliding and packing together. And in the
Is it
granular material, as you start to, sorry? Yeah?
Yeah, you go ahead. Sorry.
Okay. And in the granular material, as you start to squeeze it, they rearrange a little bit and you form new contacts until you reach a point where there's pretty much no more new contacts. You've got a tight packing, and then it's just linear for a while. And so there's rearrangement and new contacts forming. When new contacts form, it gets stiffer. Okay, it's like you've added new springs in there. Now, in the granite, the initial granite actually has all sorts of little tiny gaps and slits to begin with. Look at this is the idea. This is marble. It's a similar concept. Notice, if we actually looked at this before we tested it, these things are not perfect, these interfaces. There's all these little tiny gaps in different places. So even though they're very small, if you figure out the porosity of the initial system, it's like 0.01 or 0.2, I don't know what it is. It's like less than 1, much less than 1. But these things start to close when you start to squeeze this. And when they start to close, as soon as they close, there's a new spring. There's new surfaces. There's new stiffness. And so it's exact same physics. In a granite, you're closing up the initial microstructure, the initial cracks in there. They often just call those cracks, but they could be pores, all kinds of other stuff. You're closing those, and so it's getting stiffer. And now at this point, it's just pretty much linear, which means you've closed them all. And so that's why this first part of the loading, they call it a crack closure stage. And that's why this stress, once this thing is linear, they call that the crack closure stress. Okay. Then you keep loading. And during this period also, you can do all kinds of cool things. You can put little acoustic sensors around the surface of the specimen, and you can, every time a crack forms, you get an acoustic event, you get a little earthquake. And if you measure the arrival times of all those different places, you can back calculate the magnitude of the earthquake and where it happened. And so those earthquakes are like little micro cracks, and so you can record those things and locate those during tests. And I'm going to rely upon that information in the continuing interpretation as we move forward here. There's also interpretations of where you can take the test, run it for a while, stop the test, take thin sections, and look at things. Then you go and take the same type of rock and you run the test a little further and you look at things. That one's kind of fraught with peril because no two specimens of rock, even if you record them right next to each other, are exactly the same. But in general, you can still make comparisons. So we can determine as the test is going on what's happening here. Okay, that's what this interpretation is about. And so you hear these things often as you can actually hear this during a test. You can hear little snaps and pops. And so there's almost no snaps and pops going on here. You're basically just closing up those initial gaps. Okay, so crack closure. Then you keep going a little further so you're just applying strain and you're monitoring the force. It's getting higher and higher in a linear fashion, and you're pretty much not getting anything happen. That's why it's linear. There's pretty much no micro cracks forming, and everything's been closed up. And so you just have this structure. It's just like the granular material in that odometer test, after it's all compact in there, there's going to be a while where all it does is just push itself tighter and tighter. There's just surfaces. There's no new surfaces forming. There are all those contacts, and they're just pushing, again, a little tighter. So there's this linear portion. So they call this linear elastic right here. Okay. But there is actually evidence, even during here, that something is happening that's damaging it. And I know that because if I look at this curve, if you look really closely, this is not linear. It's linear at the first part, but this one is a little less linear. Now, if it was purely linear elastic, this is the Poisson ratio, and this would have to be straight. The fact that it's actually bulging a little more than it would if it was elastic means that there are like damages happening. There's like new surface area forming, and that's subparallel to compression. Because think of it, I squeeze it, and a little crack forms. A little crack forms. Boom. Well, that crack now opens a little bit, and it opens in the lateral direction. And if you're super carefully measuring that lateral strain on the surface, you say, oh, it's straining more than it would be if it was elastic. Okay. And also, people who do super careful tests, if you unload this thing in this region, it will not go back to exactly the same place that it was. So there's a little bit of cracking, but it's quite negligible. But at this point, look at this. Now suddenly it's bulging a lot compared to if it was elastic. Okay, and that's attributed to cracks that are forming, a lot of them. And we call this point then, that's when this starts happening quite a bit. It's called crack initiation. So we got here, okay? And where are these cracks? Well, these cracks, first of all, are almost all parallel with compression, and that's why they're contributing to extralateral strain. That's why this thing is bending over. So they're parallel with compression, and they are distributed pretty much homogeneously throughout the specimen. So they're just, one of them forms, and then another one forms a little further away, and then another one forms. And they're basically all isolated. Okay. So during this stage, from this strain to this strain, you got damage happening with cracks, but you could still unload this thing. It's okay. It can still carry load. Okay. But it's damaged. It has all these cracks in it. And this is if you do really crazy careful testing, you can pull out this point, and in a granite, this is where you actually start to get breakages of grains. They call that secondary cracking. Because what happens in a granite, you start to load it, the gaps start to close. You continue to load it. You start to get interfaces between the grains starting to break. And then you continue to load it, and you actually start to get a few of the grains actually start splitting. Okay. And of course, when a grain splits, that also, when you squeeze a grain, it splits, and the crack forms parallel to compression. So it splits apart. So it gives you, again, more expansion, gives you more change of this. So you keep loading this, and now's when it gets exciting. When you're sitting there, I've done this, sit there with the grad student who's doing the test. I've never got to do tests, but I've got to like watch some. And now it's getting exciting because for this like 10-minute period, it's pretty cool. Boom, boom. Nothing happens. Then pop, pop. You hear little cracks happening. Sometimes little pieces of the surface go flying off. And so this is called stable cracking because I could stop the test and unload it and everything. I could stop the test and hold the load constant and nothing would happen. Just sit there. Okay. Then you get this point here, which we call crack damage. What does that mean? This means that there's some serious bad stuff happening now. There's really significant damage starting to happen. In fact, it's so significant that the stress strain curve is even bending over. Look, it's not linear. It's getting softening. Okay. Right here, curve got steeper because it was getting stiffer because there were new surfaces in contact. Here, it's busting apart inside so much, it's not carrying as much load. It's starting to curve over. We call this softening. And so notice the lateral expansion. Holy smokes. You thought this was nonlinear. This guy's really expanding a lot of lateral strain. This vertical, that's an increment of stress, increment of this strain, boom, giant amount of expansion. Okay. The other way we know this is this. Remember this? We're measuring axial strain and lateral strain. We're computing volumetric strain. And notice that the volumetric strain is going up and up and up. And at this point, and remember I said it's contracting. At this point, there's so much damage happening that it actually, the specimen itself, the overall volume starts getting bigger. Because when you start going down, that means you're getting bigger. And so you can think of it as I'm loading, I'm getting small little cracks, and then I reach this critical point where it actually starts expanding. There's so much stuff. People will talk about a lot of cracks start forming, and some of these cracks actually interact with each other, forming connected bridges to create much longer cracks. Also, more grains start splitting. And the combination of all of these things means that you start getting very, very much of a result, very much expansion. Okay. And then if you keep doing the test, you eventually reach a peak. And I don't show the rest, but this is typically quite brittle, and it'll reach this point, and then it'll go like that. It'll just drop down. And that's where you need to put on your safety glasses, because that thing is often going to explode. And so this is what we call the UCS, right? So the typical rock mechanics test has all this complicated stuff going on, and we get one number out of it. We get two numbers out of it. We do it, we measure this initial slope in this linear region, and we get the slope of this curve. We call it Young's modulus. So we get the slope of that curve. We call it Poisson ratio, and we get the peak, and we call that UCS. And then we say we're done. And we say we've characterized the rock. And that's like crazy. There's much more complicated stuff going on, and all of these processes are going on for any kind of rock. They're very pronounced and very clearly describable for a granite, and there's different mechanisms along with this going on for like a sandstone. What I'm trying to get at here is you can have many different rocks that have the same E and nu and UCS. Completely different rocks. A tightly formed sandstone from a certain quarry and a granite from another quarry, and they're going to have the same UCS and they're going to have the same E and nu, which means right away that these properties are not sufficient to fully characterize the strength, the damage behavior of rock. Notice I'm not talking about modeling. This had nothing to do with modeling. That's to do with theoretical interpretation of trying to quantify rock and how it responds to stress. Okay. Which is going to mean we have to do more than just this test if we want to characterize relevant properties of rock. And we'll talk about that. Now, let me say one more thing about this curve, and this is something that many people in rock mechanics are not even aware of. Because typically you don't need to know all this stuff. If you're doing design and stuff, you really the UCS is usually probably good enough. And if you're building a structure in that sandstone that has a certain UCS, or in that granite that has a certain UCS, you don't really care what's going on here. Also, if you're building a structure like an excavation, you're going to typically design that such that the load that it ever gets is well below the UCS. So typically when you design things, you make sure the stress never gets above crack initiation. So that's good, because then it's pretty much still elastic and you're happy. Certainly things that the public is exposed to, like subway facilities that might be in rock, those things are designed so that the stresses are elastic. The stress never gets higher than this, and it's pretty much just elastic, and you don't have to worry. There's pretty much almost no damage in there, so you're really, really safe. However, in many mining situations, you do reach points way up here. And that's because if you want to mine and you want to get the stuff economically, you got to sort of stretch the envelope sometimes. So you're going to make excavations perhaps bigger, and you're going to allow this, and you're going to take advantage of the fact that this is stable here. So if your stress is up to here, yeah, there's a bunch of cracks and stuff in the wall of the excavation, but that's fine. It's just a lower safety factor. And we're willing to live with that if we're doing mining, but we want to have a higher safety factor if we're going to have public in that, like a subway. Okay, with me? Make sense?
Yep.
Yes.
Okay, cool. Now, here's a really interesting thing. Take this specimen, this Lactobane specimen. This is the curve you get. Boom. And you can take, so first of all, then you take 25 of these specimens from all the exact same place, right next to each other, maybe one giant core. And of course, if you test then all 25 in exactly the same conditions, you'll get 25 slightly different curves, but they'll be quite similar. The slopes here, which is E and nu, will have a very small variation. It might be 69, anywhere from 69 GPa, 74, 65. So the elastic stuff will be almost the same, but the peak, there's going to be a bigger variability. Okay, it might be 200 plus or minus 30 MPa. And this is because this peak stress is a function of all this crazy damage going on. When it's elastic, there pretty much doesn't matter, little tiny variations. But those 30 samples, if you did microstructural scans, are not 100% exactly the same. And this UCS is going to be sensitive to that sort of stuff. But it's the best we do. So we do this, we measure this. So a typical world in the experimental world, in the practical world, is you take as many cores as you can, maybe 30 of them, you do these tests 30 times, and you get a mean and a standard deviation for these properties you measure. And again, the only ones you typically measure is E and nu and UCS. Now, if you take this Lactobane granite specimen, there was a guy who did this in the late 80s. And he did this because the Canadian Nuclear Waste Program had a big facility near Lactobane where they had an underground research laboratory, 450 meters deep in this Lactobane granite. They made big giant tunnels, and they did all kinds of research related to the behavior of damage that forms around the tunnels. They did that because to store radioactive waste, the best thing anybody's come up with is to put it deep underground in a repository that's been stable for 1 million years geologically. So it's reasonable if we put it in there, it'll stay stable for another couple 100,000 years. That's the bottom line of radioactive waste storage. So the result is you got to really understand what's going to happen to an excavation, because that's where you're going to put the nuclear waste. So there's all this research that was done on Lactobane granite. It's probably the most studied rock that I'm aware of. And so for Lactobane granite, they did a huge amount of complicated testing so they could get this stuff here. Because this is not just a standard rock mechanics building an excavation that has to last for 10 or 20 years. This excavation for nuclear waste we got to say what's going to happen over 100,000 years. Is it going to just sit there? Maybe there's some kind of time-dependent processes going on. So to study that, there's a guy who went, and actually his grad student, I'm sure, did most of the work. They said, well, let's take this Lactobane granite. Why don't you go give us like 100 cores? So the guys out at the laboratory took 100 cores and sent them to this professor, and his grad student probably spent the whole summer running a special kind of test. So what was the test? He set up his UCS rig, just his standard UCS rig, and he slowly applied axial strain, just like this. But when he reached this point, and he knows he reached the point because he's plotting this curve that he's measuring. So when that curve starts bending over, he then would hold the load constant now. So he turns off his mechanism that's applying strain. He stops the motion and he turns on the mechanism of the servo machine that maintains constant load. Okay. And well, that's fine. It should just sit there. So he does this, and then he just, now he has to go and, I don't know, go drink a lot of coffee. And what he finds is that if he drinks enough coffee and waits long, he comes back into his lab the next morning and the whole thing is laying there on the floor. It's exploded and failed. Which means that he only loaded it up to here, and yet if you wait long enough, the rock fails. Which indicates clearly that there's a time dependence to the strength. Because this thing, the loading went from here to here in like about 10 minutes. And this time dependence is a slower process. And so what they found is that if you load it up really close to the UCS, it might only take like 10 minutes till it fails. If you load it up halfway, it might take 10 days. And the longest test they ran typically were out at 4 or 5 months. And so if they load it below this value, the longest test that have ever been run, it still hasn't failed. So this crack damage stress, when they're doing long-term design of long-term structures, like crazy long-term, 100,000 years, to be safe, they load them below this value. Okay. And so this is what's happening, and they call this unstable cracking. So what that means is if you keep running your test and you stop the platens and you wait for a while, it'll still fail. And we could talk all about this, and there's a mechanism that's called stress corrosion that is used to explain what's happening, but that's a whole separate topic. Okay, so this is the behavior that we see when you load a real rock, and this is a real curve from black dividing granite. Okay, and we won't talk about this. These are other ways of doing things to cleverly figure out where these stresses are. Okay, now let's look at probably one of the simplest possible bonded particle models, and let's look at it in light of what we just said about what we observe experimentally in a granite. So this is and I say kind of simplest, I had a student make these things, oh my God, in the very early days. We wrote the bonded particle model paper in 2004, but it was the result of work that we did for the Canadian nuclear waste people in the late 90s, early 2000s. And this is then the kind of systems we had. So this animation was made with PFC version 3 probably, and it's just disks. And now you know about this, parallel bonds, disks with parallel bonds. The disks, there's about 100 disks across and about 100 disks in the other direction. They're bonded together with parallel bonds. First, they're packed at a certain pressure. So now they've got all this network of contacts. Then we give parallel bonds. Okay, and we're going to give the parallel bonds that lambda, the radius multiplier of 1, which means they fully fill the distance between the diameters. And what else are we going to do? So that's our initial material. And then we're going to screw around here. We're going to drill out holes. So we're going to build this in a material vessel at a certain pressure, hopefully not too high, so we don't get a lot of overlap. We're going to put in parallel bonds. Then we're going to drill holes in it. And now it's just sitting there. Okay. And so now what we're going to then do is we're going to perform a 2D version of a UCS test. We're going to have a wall and a wall. And in this case, we're going to make them both move to keep everything symmetric. Okay. In the real laboratory, we typically just push this one down. And if you're loading quasi-statically, it probably doesn't really matter if you move them both slowly or just move one slowly. In super great detail, there are differences, but for most things, it doesn't matter. So this is what we're going to do. We're going to move up and down We're going to monitor the relative change of distance, divide by this initial length. That's what we're going to call axial strain on the X. We're going to take the total force acting on this wall, add it to the total force on this wall, take half of that, which is the average force, and we're going to call that the axial stress. And if we're loading slow enough, these forces should be equal and opposite. Okay, so this is just like a real UCS test. And what we're plotting here is this curve, axial stress, axial strain. Okay, and we're also, though, going to be showing where breakages of the bonds occur. And we're going to think of those as like micro cracks. Suddenly, boom, the cement breaks. There's no more resistance of force and moment. Cement, just a frictional interface now. And so every time a bond breaks, we're going to draw a little red line. And it's going to be perpendicular to the two particles. If you drew a line from center to center and you drew a perpendicular line with the same width as the parallel bond, the same length, that's what we're going to call, think of that as a micro crack. That's how we're going to visualize the damage. Okay, and what we expect, if it behaves like rock, we start expecting to see initial micro cracks forming around here. We expect to see, hopefully, everything happening here. So let's see what we get. So here's the measured stress strain curve. First of all, it's linear. It's not doing this. It's not doing this. And we speculate it's not because our initial microstructure was tightly packed and bonded everywhere. And so when we start squeezing it, there are no initial gaps and slits to fill it, to start squeezing together. So that's expected. We also expect that if we change the microstructure so that we also had initial gaps and slits, we would expect to see that, that stiffening. So we're not getting the stiffening. Look here, a bond has broken, even early on. Okay, and this is because there's a heterogeneous force distribution. We're going to look at the force chains later. So there's one bond broken. Going to keep going. Oh, whoops. Oh, come on. Let's see. Just a minute. I want to be able to run this in a more controlled way. And, oh, I can't because this stupid thing is inside the PowerPoint. Hold on. I'll get back there. Can I stop it? Good, I can. Okay, we're running it. One crack. You bloody thing. Why is it? Wait, just a second. How come I can stop it here? Okay. I think I'm just not hitting the right spot. Just a second. There's one crack.
Oh.
Am I missing this button? Why is it not letting me?
Maybe you should make that bottom always on the screen so you can.
Oh, that's what it is. Okay, I'll have to just keep doing it a lot. Okay, look at. Bloody hell. This is annoying. Maybe I can do this. Okay, I just won't move my finger. So, I'm loading it. There we go. Notice, there's a few cracks that have formed. There's some more cracks. Look at this. At this point, it's starting to drop that stress strain curve. Uh-oh. Okay. Now there's more cracks forming, and it's dropping. And there's more cracks forming, and eventually it splits in half. Let's just run that thing from the beginning. Let's go back here. Let's just let it run through. Now it's going to start cracking. And it still has some load carrying capacity. And we continue to squeeze it, but you can see it's like broken up into these columns. Now, To be perfectly connected with this lecture, I should not have drilled holes in this. The fact that there are holes in this is making it a more complicated stress field. There is not just uniform stress, okay? And that's why it's more complicated response than what I talked about. Notice what's happening here. Look in that upper left corner at the bottom of that top left hole. Do you see that crack forming, that fracture? See that? This, talking about this, okay? That starts to form. It's manifest in the fact that the measured force, it was dropping a little bit. And it's forming because when we load a circular hole in compression, it generates tension above and below. And there's high tension here, and that's what makes this fracture start to form. Okay. And the same thing has happened here. There's one that formed here and went up. This one's going. This one's bridging between the two. This side is actually blowing out. Okay. And this system now, since it's so fragmented, is not as stiff anymore as the previous system. And that's why the force that's being measured is getting smaller. Okay. Now, let's look at this in terms of this force chains. Okay. So black is compression and red is tension. Remember, when you squeeze this material for this reason, here's the general idea. Squeeze the balls, causes tension here. Those are the guys that break. So the force chains, we're going to squeeze it. There'll be black ones going through here, making a diamond, but there'll be red ones here, tension. And so that's what we're going to be plotting here. Now I know why I shouldn't embed stuff inside of here. Stop. Got it. So thickness is proportional to magnitude. This is the exact force chain thing we've been talking about. And so notice you're getting this, first of all, it's non-uniform, but you're getting this compression, that's black, inducing tension, and these are this way. Here's the stress strain curve. Now it's getting even more loaded, so things are getting thicker. Notice the red, there's tension above and below these holes. That's naturally developing because the forces are flowing around the holes. Here's the little blue. This is the force. The next thing, the parallel bond. There's some force carried between the two surfaces touching, and there's additional force carried in the cement. So we're going to do blue and black. Blue is the forces of the two surfaces touching. Black is the force in the cement. And red is the force in the cement. And so you can see now it's getting loaded up, but there's been no cracks. Stress strain curve is still linear. And now watch. You're going to see cracks forming, and you're going to see the force chains unloading in certain areas. Watch up here as this crack forms. You can see how that material is still carrying load in the center. That's why the stress strain curve has not dropped all the way to 0. Okay. Look at it again. When this left side fails here, this is going to get unloaded because it's not stiff anymore. It's just pushing out. There's still load carried here. This is how actually pillars in mines fail. As you load a pillar, a giant pillar, like 10 meters across, it starts to fail on the outside. And the failure slowly works its way inside. Because rock, if you have confinement, gets stronger. So the inside of the pillar is still confined, whereas the free surfaces are not confined. So we're seeing these secondary effects. Most of what I'm discussing here is like a secondary effect based on that lower level stuff that's happening just in the base material itself. Okay. So this is the fundamental behavior of a bonded material, just a simple bonded material, parallel bonded. And so what mechanisms, it's not doing the closure. It's doing linear behavior for a while. And then you start getting these cracks and it's still able to carry more load. And then eventually it breaks. Okay. So that's what I'm illustrating in these pictures. Let's just talk this through. So again, this is the key thing: heterogeneity, induced local tension, compression and tension. This is later on in the test. This has already begun to, is not stiff anymore. The load is being carried mostly right here, right? These are the broken bonds in cyan. They have just coalesced into what, if I was going to interpret this, in a continuum way, I would call that a fracture. I would say, oh, let's think of this as a linear elastic body with a big giant crack, which I'll call a fracture. And let's interpret it that way. I don't need to interpret anything here. This is just naturally happening, and it's localizing. So you get these broken bonds. You can see how the force chains are not thick anymore. There's hardly any load being carried in that, because basically it's cracked off here and it's cracked through here. So this stuff is just basically pushing itself down. So it's unloading, but it's still carrying load in the middle. That's what it says here. There's still load carried in this stiff chain of largely uncracked material, but there is some cracks in here. And then this is that secondary effect. Because we have those holes, they naturally produce tension above and below, which makes these cracks initiate and grow upwards. This is also what you find in experiments that are done on rock that has holes. They start to fail above and below, and then the macroscopic fractures line up with compression. And we call this axial splitting. This is what we observe in the laboratory for UCS tests mostly. You see these columns of material and it breaks into columns. If you modify the UCS test so you apply confining pressure to the surface of the sides of the cylinder, then you inhibit this axial splitting, and instead you eventually get a shear fracture that forms at a macro scale. And it also forms at a higher stress. Okay. What are we going to say? Yes. What do you think? This makes sense? Do you get the idea? Oh, I just spilled my coffee. Do you get the idea?
Yep.
Okay. Hold on. I've got coffee running all over my desk. Just a minute here. Fortunately, I'm the kind of guy that actually has a handkerchief in my pocket. Oh my, hang on. I've saturated my handkerchief. I think we're good enough. Okay. So this is essentially the justification that is arguing that these bonded systems, these bonded particle models, are reproducing the essential features of as rock is damaged. Okay. And we've only talked about compression here. But it gives you the idea, right? And you could, I think, see, you don't have to have, these particles could be polygonal, and now they're going to be more interlocked. And so that's going to affect things, right? These particles, and these particles don't have to be bonded particle models. Each of those particles could be a little triangle that's part of a big finite element mesh of a continuum, and you could have those interfaces breaking. We're going to talk about that a little next week, which is something called the FDEM model, finite discrete element method model. The key thing is if you have a system of components that exhibit tension when you squeeze it, heterogeneity-induced local tension, that is the important mechanism that's driving all the actual damage processes in the rock. Okay. And so to sum this all up, when you have a bonded particle model, what you are doing is there's really two things. You're not only nucleating microcracks, these isolated breakages, but you're also allowing for those things to localize. Those big giant things can form, and you're getting them to interact. Because in the end, the specimen fails because they interact. And we're getting all of that evolution in a BPM. And that is going to allow us to look at different microstructures because all those things can be built into the model, right? And you could think of those as microstructural features, right? So we could construct the bonded particle models in different ways to create this microstructure or to create that microstructure, right? And that's why I say this is extremely rich. This is very much the fundamental physics of how rock breaks at the grain scale. And what I mean by that is we're thinking of everything in terms of the lens of damage is all happening in terms of the grains and what's going on between the grains. We could extend our analysis and go 2 orders of magnitude deeper in and zoom in, and we could look inside a grain. And inside that grain, there also may be damage processes going on at an even lower scale. For most rock mechanics problems, we're able to work at what I call the grain scale. And so we can put in these grain scale discontinuities. And this is where I mean there's rich areas of further exploration of what different, like how do we build this kind of microstructure? So all kinds of different clever ways people can use these types of models to build such things and look at them, and people are doing that. Okay. Couple more slides. This is a high-level picture, then we'll take a break. And I may have shown this before, but maybe a second time might be helpful to hear it again. So again, we're talking now about how can I idealize a rock, and there's different ways to think about it. And one way is a continuum model, and one way is a bonded particle model, right? And so on the left, we're going to assume that there's a theory called continuum mechanics and theory of elasticity and fracture mechanics, and we can interpret everything. We can make a continuum, and that means we have elements and nodes. Remember the shell thing? We had elements and nodes. It's the same thing. It's a continuum model. And so in this world, the way that we get damage is we put in a constitutive model. This is what we choose. So if we want to model a certain rock, we give it a certain curve here. Okay. If it's just linear elastic, the curve is simple. It's a straight line. And if you unload it, it goes back to nothing. There's no damage. The fact that this curve, this is a macroscopic thing that's measured in a macroscopic test, goes up and now it starts softening and starts to fail. Well, we basically build that stress strain response into each element. So each element individually satisfies this. Okay. And that's what I mean by we enforce continuum behavior. That's what we have. We call these things constitutive models. FLAC3D has maybe one of the most comprehensive set of constitutive models for rock failure. I don't know. There's probably at least 12, maybe 15 different ones. Sandstones have certain type of constitutive models that reproduce pretty much behavior sandstone, because remember, sandstone has pore collapse. So there's stuff that starts to happen. It's much more complicated than just the granite. Other types of rock have different constitutive models. So you choose the constitutive model based on the kind of rock to try to model that. Okay. In this system, it's a lower level thing. You're actually going down to the level of particles and contacts. And you have essentially the constitutive model, instead of being stress strain, is force displacement at each contact. Just like here, it's stress strain at each element, and each one tracks its own thing. Here, each contact tracks its own place on this curve. This is my simplest possible nonlinear curve. This is actually a brittle. This is not brittle. This is actually a granular system. Remember, shear force goes up, slides, unloads, right? We could show a parallel bond curve, which would be, a bonded system, but you get the idea. There's a contact model, and that's where the action's happening. And so I call this, it's particulate behavior. It's not continuum behavior. We never use stress and strain. That's why I mentioned this is, if Isaac Newton had this available, the way we looked at material at that time, the concepts of stress and strain did not exist. So this is how everything would have been was interpreted by Newton. And because we're modeling at this level, we can change all different aspects of the microstructure. And then once we do, we can measure the macroscopic response, and that is the constitutive response, which we then could take and put into a new constitutive model. And many people do that. They might say, oh, I have a material there. It's so weird, this rock. It has these strange inclusions that are lined in a certain way. And it has all sorts of weird pores, and it has this and that. And so they could say, well, I'm going to build microstructural models of that, and I'm going to measure the macroscopic responses, and then I'm going to give some cool thinking to it, and I'm going to pull out the essential features of that, and I'm going to build a constitutive model. And many people do that because they're able to take the synthetic system and treat it like an experimental, like a real experiment, and run the same tests synthetically as they would in an experiment, and then they can interpret this and turn it into a constitutive model. This is still done a lot because computational requirements are still high for this. And so if you actually build a material at the true grain size, so if we were modeling that granite, each of these things, that lactobonate granite, this is between like 1 and 4 millimeter diameter grains. So if we just had 4 millimeter ball, then beach ball is a grain, right? And if we have a specimen that's 50, it's going to take like 200 of these or something like that, right? So maybe we could directly model a specimen of rock, but if we wanted to model an entire excavation where the excavation is like 4 meter diameter, we just don't have enough capability to do that. So what people will typically then do is use a continuum model with some kind of constitutive model to actually do those analyses. But computer power keeps getting more and more, there gets to be more and more robust, and not robust, but more powerful. We can do bigger models now. And so we're beginning to do boundary value problems with bonded particle systems directly. Or we do excavation problems, but in the region of interest where the damage might happen around the excavation, then we put in a bonded system. We we could say like, let's remove this element. And now if we took at this system and squeeze it, it's like a big cavern in there. And maybe all the damage happens typically just on the sides. So then we could go and take this region and fill it with a bunch of bonded particles and effectively have a proper interface so it's glued together to the continuum. And we call that a coupled model, and people do that, and we do that with PFC. And so that way we can study in detail some of these complicated damage processes that occur at the excavation scale. We can study them by building microstructural models and embedding those in a bigger continuum so that we get the right boundary conditions. Okay. I think that's it. There we go. Thoughts? Thoughts? Someone's got to give me a thought. You guys got to save Sheehan because I'm going to pick on him if no one else jumps in. Ayat, what do you think about this?
I'm just like, you said we can build both of those in PFC, so I would like to know more about that. When you said we remove the nodes and in the continuum model, and we add a layer of bounded particles. So I'm just curious because when I started first in PhD, Dr. Rashenka was telling me at some point we need to use the couple FEM, DEM modeling. So I'm curious to know if PFC do that.
Okay. It does that. You can do that. It's actually quite easy to do it relatively. It's built into PFC. And you and I can talk about that since I'm working with you on your research, but it's,
Yes.
I can't really talk about it now in detail.
Okay.
But the basic idea is simple. The basic idea, think if you had this model. No, here.
Mhm.
My belief is anything you should be able to explain in a few words. Okay, this is a big system, but think
Yes.
there's not just 9, but a whole ton of these, and I'm squeezing it.
Mhm.
And now let's say, now I just changed the system. I just pulled it. The element's not here. Okay, so now when I squeeze this, the force the traction that used to go across here can't go anywhere. It's a free surface, so that force has to flow around, and this system will behave like a big giant square shaped excavation. Nothing there. Okay.
Yes.
I haven't done anything to the continuum model except remove an element, right? And I could have, if this was bigger, I could have removed a whole pile of elements that are all together, right? And then I have an opening in the mesh. We call this a mesh.
Mhm.
So now what I could do separately is I could build a PFC model like this, and I'll make this PFC model be exactly the same shape and size as that opening. Okay, you with me? I build the bounded
Yes.
particle model just like this. Then what I could do is I could take that thing and I could place it in this hole. Okay. And if I placed it in this hole, then we just have to work out what kind of information goes back and forth across those boundaries to make this thing behave as if it was really in there. So think about this. This system has a hole. I squeeze it. That means that these boundary edges are going to move. They're going to deform inward.
Mhm.
The top and bottom are going to go down. The outside ones are going to squeeze. Well, no, that's not what it's going to do. It's going to basically, it's an excavation. It's not a solid thing. It's going to move. Okay. The general idea, there's a hole in the mesh. You squeeze it. The boundary's going to move. There's going to be displacement.
Mhm.
So, and when there's displacement, this element is going to push back. The material in here is going to push back. So there's going to be traction around here pushing back. Okay. Take this system in PFC. See, there's a wall here. There's 4 walls. Let's go and take this wall, and let's say we're going to have a special command. Boom. Build, put PFC inside of continuum. Special command. You give it this. What it's going to do, it's going to take this wall, and it's going to force this wall to deform exactly like this element edge. Okay. And we can do this for a general shape. We just have a bunch of walls. We have to always enclose the PFC with a bunch of walls. And so those walls will fit the shape of the removed elements. Okay. Then those walls are going to be slaved so that they move just like this guy. And meanwhile, so far, when this guy deforms, PFC gets loaded because the walls move. And as soon as the walls move, PFC naturally builds up forces, right?
Mhm.
So that's coupling one way. The continuum code is making PFC get loaded. Now, the thing that the continuum code, though, is along each wall, there's going to be a resultant force from all the guys pushing it. There's a force, normal and shear. Well, that force, if you divide by the area, is a traction. So there's a traction boundary condition applied to each edge. So this guy There's no element there, but instead the element is removed, but there's a traction here and a traction here. Traction is force over surface. So, and these are coupled then. So a time step in one is the same as a time step in the other. So this guy deforms, it moves the edges. The edges push against PFC. PFC builds up force. The force then gets applied as a boundary condition to the boundary. And so everything is in synchronization. We end up having full coupling. Does that kind of make sense?
Yes.
Okay. That's essentially what we do. And so that allows us then to embed PFC in a big, larger continuum. And we do this, that's built into our codes. That means you have to have, in addition to PFC, you have to have some continuum model. And since we're going to build this in, well, our continuum model is going to be FLAC 3D.
Okay.
And so PFC 3D and FLAC 3D have this coupling methodology that I just described, like built into them. So if you have both codes, it's quite easy to do what I just said.
Okay. Thank you.
Yeah. So that's the idea. It worked quite brilliantly. Okay, that's your thought. Who else? Okay, Shihang, I'm nailing you.
Okay.
What's your thought about all this?
Okay, every time I saw these pictures, it always reminds me of one coupling method. Maybe you've heard it. The MPM, the coupling method of MPM and DEM. The material MPM, just the material point method. Yeah.
Correct.
And DEM. So the primary thought of this method is they use we look at the left panel, like in this continuum model, and we have element which is a square, and in each element we need to have a constitutive model. Well, in this coupling method, they use the DEM to represent DEM to calculate a special they use the DEM model, like the right panel, and they derive the constitutive model for each element. And they think this method would provide a better like praise, accuracy maybe, and lower errors since if you use the like elastic model or original or simple plastic constitutive model, it would be a little bit do not behave that. I always forget that word. Okay, so this is the main thoughts of that. They use the DEM model to derive the constitutive model and use it in the MPM, and this is the full coupling circle. And I think it's theoretically I think it's perfect. Maybe it really solved the computational cost of the DEM, and it can also handle the large deformation with the MPM. So I do not read a lot of paper from this. The main author is from the Hong Kong University of the Hong Kong. Wait a sec. The Hong Kong University of Science and Technology. The professor Jidong Zhao. Maybe you read some of these papers.
Okay.
Yeah.
Okay. Yes. I mean, yeah, what you're talking about is, exactly this concept, right? The fact that the bonded particle system lets you put in a microstructure and gives you stress-strain response. And that can be very realistic and complicated stress-strain response. Yeah, and then this is a way you're talking about of hooking that in to another type of continuum model, shall we say, MPM. Yes, good.
Yeah, that's all.
Okay. Yun King, what do you think? This makes sense? Blowing your mind?
Well, and actually I'm thinking about some similar thing, but actually I don't know about the MPM. So yeah, and actually I'm thinking about that. Can we find some like rules of the size effect so that we can use some small model with the bounded particle, but model the engineering size thing? Yeah, well, I think it's quite similar with what Shihang said. We use some kind of MPM thing, but actually I don't know about that. So yeah, this is what I'm thinking about.
Okay. Well, yeah, that's like a latest research type thing. You can hook it in with MPM, but you can also trivially hook it in with any continuum finite element model or with FLAC3D, which is a continuum model. Good. Okay. Yeah, what I also want to get at is that you're already sort of all assuming this model makes sense and that you can put in microstructures and you get reasonable behavior. And I'm, the talk has been tried to build up a case that this is a reasonable model for microstructure, and it does give you the mechanisms that occur there. And thus, it's warranted to use such a model to do these next level things. Basically, when you have a system that has this rock that has complicated damage processes, and you don't really understand them in 100% detailed way to map it into some constitutive model, you can directly model the microstructure and simply observe the resulting behavior. So, okay, let's take a calibrating. All right. Let's actually talk. Remember, we talked about two fundamental. Yeah?
I have a question. In fact,
oh, please.
This is an explanation of Aya's question. It's about the calibration of the microparameters. We know that the parameters of macroparameter, or the calibration of microparameters has strong size effects. If we change the size or even the distribution of particles, the macroparameters need to be recalibrated. If I use the FDEM to simulate an engineering scale model, how should I calibrate the contact parameters? Because the contact parameters are usually calibrated through rock samples, the particle size here is much smaller than that in the engineering scale model, and the distribution is also different.
Yes. Okay, your question is right on the mark. I don't know the answer. Nobody in the world knows the answer. That's why I talk about this as a microstructural model. Doesn't mean I don't have ways to deal with this, but it doesn't mean I know the answer. So to rephrase the question to see if I understand it and to see if everyone else understands it, Bowen pointed out that when we calibrate a bonded particle model, we have to choose a specimen size and we have to choose a particle size. And ideally, we make the particle size the same as the real particles and the specimen the same as the real specimen. And that's what we're going to be able to do for lab specimens. But if we then want to build a bonded system to represent like a hunk of material around a big giant excavation, we still are, even if we embed it in a continuum, we typically still are going to have to make the particles bigger. And some of the macroscopic properties are sensitive to particle size. And so the question is, what the heck do we do? The quick answer is I typically would calibrate things at the, well, what people typically do is they work with the particle size of their final model that they care about. And then they take specimens of rock that are big. So it's like, oh, I have an excavation that's 4 meters in diameter. Well, I'm going to take I'm going to take a UCS test that's an 8 meter by 4 meter hunk of cylinder, and I'm going to perform a UCS test on that, and I'm going to use that to do the calibration. That way, at least you're matching properties with that you think are important in the model you're doing. But it raises all kinds of other weird points. One, no one can ever do a lab test on an 8 meter by 4 meter cube of the real rock. And at the excavation scale, if you really were to take out an 8 by 4 meter cylinder of rock, when you tested that, it would not behave like a laboratory scale cylinder of the same rock. And the reason is because the laboratory scale cylinder has been selected to be a perfect intact hunk of the material. You go through your core with all these cylinders, and there's a bunch of them that like cut through joints and that break apart and all this. You just take the good ones and you test those. So those are those are intact rock. But at the scale of 8 by 4 meters, that rock is going to have some sort of joints. It's going to have other structures at a bigger level, which is going to make it weaker than if that wasn't there. And we call this rock mass scale versus laboratory scale. And people in general, what you will find if you calibrate a PFC material at the laboratory scale and make it match, but then if you use those same micro properties where you've made everything, all the particles bigger, it will be too strong. And you will have to degrade them somehow to make it match the response of the rock. And people do the same thing in continuum models. When they're looking at damage around an excavation, they use constitutive properties that are supposed to correspond with a rock mass scale system. Think of like a big hunk of rock. If there's no joints in it and it's intact, it'll have a 200 MPa UCS. If you put a whole bunch of joints in it, it's going to be a lot weaker. And at the rock mass scale, it's going to have stuff like that in it. And the way of dealing with this, you could refer to this as a size effect as you go from lab scale to rock mass scale, is an open issue. It's an open research issue. There are different ways people have come up with to try to deal with this, because people deal with it all the time. Anybody who's using any kind of rock mechanics model, continuum or bonded, when they're making predictions at excavation scale, or even bigger, like a slope scale, they have to use rock mass properties. And what the hell do you do? How do you do those? And there are ad hoc ways that people who are expert consultants who do these kind of models use. Their ad hoc ways to do that. There's ways of what they call upscaling. Like the people at Itasca are doing state-of-the-art rock mechanics simulations. They're not working at laboratory scale. They're looking at real problems that are at excavation or above scale. And so they have to do things to reduce the properties they put in. Like the Young's modulus they put into a continuum model is a lot less than the Young's modulus that someone measures in an intact sample. And that's all I'm going to say at this stage. It's an open question, so there is no simple answer. Okay?
Oh, okay. Thank you.
Okay, yeah. Again, yeah, that's right on the mark. That's exactly a big point. What we're going to talk about here is the starting point. You first have to get this right for an intact system before you can start going around and making it even more complicated. And a good example of the rock mass business is this, right? This is a rock mass scale. This is 1 meter by 1 meter. This is a rock that actually has all sorts of pores in it. This is a real rock. It's called lithophysal tuff. There's a whole talk I can give about this. The reason we built this model, because nuclear waste was originally going to be stored in the United States in a place called Yucca Mountain. And the repository deep underground has rock that has all these lithophysal cavities. And so we tried to understand the effect of the lithophysal cavities at how it affects the overall macroscopic properties of the rock, because that's what they have to feed in to the giant continuum models that they use to make predictions. And they can hardly get any cores big enough to look at the effect of these lithophysi. So we use this type of model to do that. So this is an example. This is like this material here is, is naturally going to be weaker because of that. So in this case, we built a bonded system that we calibrated to behave like an intact rock, and then we simply put holes in it, and it gave us all kinds of weaker response, which then was actually used as input data to figure out what the weaker response is that they think of the real rock is. But I'm saying this because it's an example. This is a size effect here. The bigger scale, right? When we do a lab test, this is 1 meter. When we do a lab test, we carve out a core right in here. So it's going to be stronger than at this scale. When we measure properties at this scale, it's weaker. Okay. Excellent. I wanted to try and answer your question because it's terrible if I just say, don't worry, we'll talk about it later, because you usually never get back to it. Okay, we're back. We're back. All right. Yet again, because I'm really trying to go at a pace everyone can understand, we're most likely gonna have 2 more lectures, but we'll see. But I'm not going to speed things up because it doesn't help at all if I just suddenly start going crazy and go super fast. So we'll see where we get and we'll reevaluate. Okay, I talked about rock. Rock is this weird thing. Amorphous particles joined by varying amounts of cementing material, amorphous particles and crystals. And we can break it into, at the high level, compact and porous types of rock. And an example of compact is granite, and an example of porous is sandstone. And so that's the lens that we're going to use to try to look at this. And because of the question Bowen just raised, notice everything we're talking about here is intact. This is a thing sitting on my desk. This is a cool little sandstone thing. You can see how it's sandstone. You can, if you scrub it with your fingernail, you can rip off some grains, right? There's my pocket knife, length scale. This is, again, in my office, this is actually lactobonded granite, because I've sort of indirectly talked about the whole reason we even had the funding to develop the bonded particle model was because we did a lot of research in the late 1990s for the Canadian nuclear waste people, and they did all this work with lactobonded granite. And this is, notice my length scale here. This is because this must be centimeters here. So I'm assuming then this is 50 millimeters. So this is a bigger specimen. This was a big 150 millimeter diameter specimen of lactobonded granite, and they did a UCS test on it. They loaded this thing really, really slow. And this is how it failed. This little chunk here is that chunk. So it's a bigger specimen. And it failed by eventually breaking in 2 pieces, where the failure surface is at like an angle here. And typically when people interpret this, they say, oh, that's a shear failure. Because at this scale of the sample, if you draw a line here at the fracture surface, well, the top part moved to the left and the bottom part didn't move. So that means it's a shear motion, and this is a shear fracture. But if you actually zoom in, and you go to the grain scale, that so-called macro shear fracture is actually a whole bunch of tiny tensile cracks that are aligned parallel to the direction of loading. And you can see them here. See this guy? See this guy? See this guy? It's a whole bunch of tensile cracks that have localized into a diagonally oriented surface. And then once that surface forms, we now get shear loading. So again, the actual breakage that's happening at the grain scale is tensile breakage. Okay. So let's talk about these rocks a little bit more here. We're talking about microstructure, so we got to understand a little bit more about them. And so here actually is a very big summary of, like, here's granite. It's super interlocked. And why is that? It's because these suckers here are crystals. These things we call grains, in this case, are crystals. Remember, rock, crystals and amorphous particles. These are crystals. How do crystals form? You have a melt of magma down here, a melt of magma. And here's my magma. It's a silicate type stuff in there. It's really hot and it's under high pressure deep in the earth. And you get these sites that are the seed points whereby growth occurs and things start growing outward and it starts forming itself. It's like it's a self-assembly process. Each one of these starts forming a crystal. And that crystal grows outward from that seed location. And then it starts to bump against the neighboring crystals. And you get the idea here, right? Finally, everybody, pretty much all the space is filled. That's why this has almost no porosity. When it perfectly crystallizes, there's no porosity. There's no gaps or slits or anything. If it perfectly crystallizes, this requires very slow cooling of the system. If you cool it really, really fast, you get a different kind of microstructure because it doesn't have time for everybody to make this system here, this interlocked network. Okay, and that's why you get these crazy shapes. And notice that these crazy shapes of granite are by no means polygons. They're not convex polygons. They're worse. They're even weirder shapes. Even in this cartoon, you can see these shapes. They're all crazy shapes here. So they're crazy shapes, and they're also super interlocked. The reason that the granite, when you take the core and do a UCS test on it, has that initial microcrack fabric that closes, that's what makes it stiffen, is because this thing might have formed 4 million years ago. And now it's been sitting down there, and typically it's been slowly upraised till you get to the, 200-300 meters underground or even to the surface. And during that process, there is damage that's occurring to this material because the stress at this point when it's crystallizing, there's very high compressive stresses in this system. So it's highly compressed and now it locks itself together. As it starts moving upward in the earth, the pressure on the boundary gets less and less. So it actually starts to expand elastically. And it starts to cause all kinds of weird heterogeneous local forces. Just like it's a heterogeneous assembly. When you squeeze it from the outside, you get weird tensions. If you let it unsqueeze, you also get weird tensions all over the place. So that's one of the reasons why the granite, when you actually get the core in your lab, has damage in it, has those slits and gaps. Okay, so that's the granite. That's like one extreme. Here's the marble, which is kind of in between. The marble is a different system. These crystals have formed in a different way. These are also crystals, but they formed in a way so that these are mostly convex polygons. And what they are is you start with a limestone. You know, a limestone, if you have a big tropical sea and you have all these little sea creatures and they die and their shells fall to the ground, to the bottom of the water, and that thing slowly builds up like a huge amount, like tens or hundreds of meters over an insane amount of time. And those things get all crushed together, and that's what limestone is. And then if you take limestone and you bury it even deeper and you squeeze it even harder and with more pressure, it goes through a process called metamorphism, and that's what produces this craziness. So this is actually little shells of sea creatures that are squeezed together and then are even squeezed more and heated even more, and they form a crystallization system like this. It's crazy. Look at the length scale, 250 microns. So that's like 2 millimeters. So you can actually see this in the marble. This is, next time you're at your home, you might have a marble countertop. Look at the marble countertop. The reason people think it's so cool is it looks cool because it has this structure in it. Sometimes you have a granite countertop. It'll have this structure. Look at these things. Next time you're in such a place, you'll notice, oh, wow, they're a little bit different. And now you have a totally different microstructure for a sandstone because that's, again, the diagenetic process to create it is different. And here, you typically have a granite that you start with. And it's an existing granite, like on the surface of the earth. And through weathering processes, it starts breaking up into little tiny pieces. Those pieces typically get washed into creeks, pushed down creeks, and deposited like in the ocean. If the creek or river flows into the ocean, they get deposited. They form an enormous deep layers of these rock fragments. They get pushed underground and they get pressurized, and various chemical processes occur as fluid goes through, and they get somehow cemented together. And then they get, again, raised up through diagenetic processes, depending on, or maybe they didn't get raised up and you care about them deep underground. They're still like that, like if you're doing oil drilling. But then these things are crazy here. Then they look like this, right? You got these weird shapes. Talk about angular or sub-rounded. I think sub-rounded means it's kind of like the angles have been worn off a little bit. Because this is often, if they formed through these fragments, get washed down creeks and rivers, they get tumbled and a lot of the angularness breaks off and then they get deposited. And so then, depending on the conditions, you end up with this very interesting microstructure that has all sorts of porosity in there. And it has places where it's been pushed and fused together. That's like the cement, right? And again, it got created and then it went through another few million years often until it gets into your laboratory to do the test. And so, this guy has already got breakages around these grains. You can see the breakage here. You can see the breakage here, right? So this is the kind of thing we want to do. In principle, each of these microstructures at this scale could be created with a bonded particle model. Only some of them in the most simplified ways have been at this point. So there's your granite. This is your sandstone. I'm also showing you the sandstone stuff because just an example of like, I do research. You're doing research, right? This is the kind of crazy stuff that I do. I read as many papers as I can without losing my mind. And at least the way I organize things is in the paper, I make a few PowerPoint slides. Here's the name of the paper. And here's the key takeaway points. And I'm a very visual guy, so I'm always trying to get the key figures. And usually most of these kind of papers often will have key figures in there, right? Where the person has thought a lot about it. What's a couple of figures that really summarize the idea? So this is the way I do it, right? So I just pulled this out of my my own research pile here, right? And so you see these are cross sections, 500 microns, right? And you can see the grains, and you can see weird stuff between the grains, and you can see porosity. This is 1 millimeter length scale. This is what it looks like if you just hold it in your hand, right? And then you load it and you start getting, it's crazy. Look at this. You squeeze these grains together. This guy split. This guy started crushing, and it's kind of fracturing, but it's a crushing zone, right? This is another good example, crushing. And so, again, oftentimes the rock already has this in it, okay? So it's the idea. Now, let's talk about this. So rock is this complicated thing, but we're doing rock mechanics and we need to make predictions of how the rock's going to behave. And so that then means, how do we characterize these rocks? How do we differentiate between them so we can say this one's stronger than another? Or this one's stiffer than another, right? And so based on our understanding of mechanics, and this is pretty much theory of elasticity thinking, again, if this question was asked to someone in 1690, right after Newton figured out F equals ma, and after Hooke figured out that there's a stiffness, this question would have been answered very differently, right? Because we don't have concepts of stress and strain yet, right? But we could still answer this question. You could say, well, you go to the quarry and you carve out a piece of it and you squeeze it and you measure the force at which it breaks, right? And some of the stuff, it's going to be obvious. Some of it's going to take a lot more force to break. And then you say, oh, it's stronger, right? And if you know about the work that Hooke has done, where you can, I mean, even a caveman, I think, would do this, the breakage thing, right? The more you press it, it takes more pressure to break it, right? Just put it in your hand and squeeze it. And then Hooke comes along and says, oh, we can measure stiffness. We squeeze it and we also measure how much we have to push it to squeeze it. Oh, that's stiffness. So that's another property. Oh, this rock is stiffer than the other one. And the thing we find at that level of thinking is that typically stiffer rocks are stronger. And that would be partly attributable to this. This thing's going to be super stiff, whereas this thing is going to be sliding a little bit and have pores, and it's probably going to be less stiff. And as a result, and also this will be stronger than that. This is like a general correlation, right? So notice there's two fundamental things we think about. We think about the strength and we think about the deformability. And strength is a little slippery concept, right? What do we mean by strength? Strength has a concept of like breakage, failure, and it depends then on how the material fails to figure out what we mean by strength. Do you remember that shell thing I showed, that circular plate with pressure? Well, that thing keeps getting more and more pressured, and eventually you reach a certain pressure. It doesn't break. It just, the pressure displacement curve just goes flat. So that's a certain type of failure. So you could say that was the critical value of pressure. So we're going to call that the strength, right? In a rock, it's going to go up, like in a UCS test for a granite, it's going to go up and it's going to drop down very quickly. We say that's the strength, right? If we load the rock differently, it's going to have different strength. If we put it in a triaxial cell and we squeeze it and measure the force at which it starts dropping down, it's going to get bigger and bigger and bigger the more it's confined. So that would be strength, right? We could take that rock and put it in a direct shear machine and slide the top and bottom surfaces in different directions and force a fracture to form along it. And that could be the point at which that happens. It's going to be an abrupt thing. It's going to load, 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 and then crack. It's going to break apart. That'll be a strength. We could call that a strength, right? We could take the rock and machine in a crack, and now we could pull it. And at some point, boom, it would rupture and the crack would shoot across both surfaces. We could call that the strength. Notice that that thing is loaded in tension. It's a different kind of strength. If it's loaded in compression, maybe we use UCS. I could go on. I haven't elucidated all the different rock mechanics tests. Each of the tests has been designed to try and talk about what's the relevant property. So if you're going to build, I don't know, let's say you didn't know much and you wanted to build a structure that could hang off the ceiling and you just had rock as a thing you could use to connect the ceiling to your structure. Well, if that's what you're concerned with, that means you're going to be pulling that in tension. And so then you would say, oh, let's do a tension test. That's the strength that matters, right? Things like that. That's what I mean, okay? So what that then means is that we have to, because there's an insanely large number of these, we have to decide which ones we think are the at least first pass important ones that we need to get right with our models. And that, again, that depends on what we're going to ask our models to do, right? Are you guys with me again? My headphones.
Oh yeah,
now
I hear you.
Okay. You with me? You get me up to where I was? Like, depends on the properties depend upon what we're going to ask the model to predict. Okay. Yeah.
Okay.
With me? You've been hearing all that. I just want to make sure I haven't been talking to myself. Okay. So now I'm going to switch and draw some stuff and talk a little bit, pull this out a little bit more. I'm going to suggest a set of properties that are important for matching if you want to have a reasonable model of a rock, Okay. These are going to be simple macroscopic properties from a few simple tests. Okay. And these are the ones we think are important. Okay. And then we're going to talk about, okay, if those are the properties, first, what are those properties? And if those are the properties, how can we go about building bonded particle models to match those? Okay. And yeah, that's what we need to do. So I'm going to switch over here and share the screen. Share the screen. Start the broadcast. Boom. In 2, 1. If all is well, can you see?
Yeah, we can see it now.
Okay. And do you see my hello?
Yep.
Fantastic. Now, is my pen working? Oh, come on. Whoops, just a second. Oh. The pen's working, right?
Yep.
Good. Okay. All right. Let's talk about some of these things. If you remember, we talked about there's two sort of classes of properties, deformability and strength. So let's talk about this one first. This is a little simpler. You squeeze it and it bulges and it moves and forces. You have to apply forces to make it squeeze, make it deform. How do we measure that? So the simplest way I could think of is we're just going to take a specimen, make it be a cylinder, and somehow we're going to glue something to it on the top and bottom. We're going to fix this, and we're going to apply a force, let's call it P, right? This is what like a caveman would do. Well, they would have done a compression. They couldn't have figured this out probably, but maybe they would. P, and we're going to measure delta, right? And we start at 0. And what are we going to do? We're going to start pulling it. And so it's going to start going up. And then we're going to stop the test. It's going to be nowhere near failure. And if we take this, and now we say, okay, so if we take this, and we were living in the time of Newton and Hooke, we would be measuring a slope, which would be a stiffness. Because stiffness relates force to displacement. That would be a stiffness. But we're not going to do it that way. People now think of things in terms of continuum mechanics, which has concepts of stress and strain. Okay. And what we're going to do is take this and we're going to compute a stress and a strain. And you know about this, right? Stress is going to be P over A. Strain is going to be delta over L naught. Right? You with me? L naught, delta, area. Okay. Yeah. And then it's still going to look linear. But what's this slope? What is the slope of that? For these conditions, what's that slope? What property is it?
E?
Mm-hmm. Remember, we talked about Young. He was a really smart guy, but he couldn't teach worth anything. Young's modulus, okay? And we're going to argue that that's a fundamental property that characterizes a material, okay? And in fact, my son is a sophomore at University of Wisconsin-Madison in mechanical engineering, and I was talking to him the other night, and he warmed my heart because he says, "Dad, I'm taking this mechanics class, and they told me that there's only 2 parameters that characterize any kind of material, and we get them from doing these little tests." So that's the question. One of the parameters, one of the properties, we're going to call it, is E, and the other property is what? What is the other property that we can measure in this test that is critical to describing how a material deforms? What is it?
Nu, Poisson's ratio?
Correct. So in this same test, this is strain. So if we plot, and we're going to call it A now for axial strain, and then we're going to call this radial strain. And so if we plot radial strain versus axial strain, this thing is going to go up, and it's also going to be linear. And this is going to be, I'm putting minus Poisson ratio because it's Poisson ratio is minus the radial strain over the axial strain. Because if axial is positive, making it shorter, it typically makes it bulge out. And they call that Poisson ratio. And so these are things we do this, kind of the simplest test I can think of, and we interpret the deformation in terms of Poisson ratio and Young's modulus. Now, what's an assumption about this? Wait, help me. I'm trying to wait before we get to that. How do I move this screen? I'm trying to hit it with my finger and pull it up.
2 fingers.
2 fingers together.
2 fingers. Oh my God. Awesome. Thank you. Okay. What is an assumption about this Ian New business here? Any ideas? There's a big assumption here.
That the material is elastic?
That's part of it, correct? It assumes that the material, again, we're using continuum mechanics to think about everything. That's the lens. Continuum mechanics has a concept of elastic response. And what that means is that if you load something, sorry?
It's not gonna fracture?
That means it's not gonna fracture, but it doesn't even care about that. What it means is that if you're measuring, if you apply some displacement and measure the force, if you let go, and the displacement will go back to 0 when the force goes back to 0. So you could stretch this, and you could measure P delta, and if it's certain materials are going to go like this, and then when they're going to go like, just a second. Wait, that's not what I meant. Hang on. Certain materials like rubber are going to do something like this. Notice that's not linear, but when you unload it, it's going to follow the same path and go to 0. Okay, if you take, people used to have rubber erasers that are, like 2 inches by a ½ inch. A rubber eraser, if you squeeze that between your fingers and you actually carefully measure what it's doing, it's going to be non-linear elastic. Not linear, but it's still elastic. It means that when you unload it, it goes back to 0. That means that when you're pushing it, it's storing energy as strain energy. And when you release the push, the strain energy all gets recovered. And that's why it doesn't change shape. Okay, so that's elastic. We assume it's elastic. So again, if it's non-linear elastic, well, now the slope is changing all the time. So there is not a single Young's modulus. Wait just a second. I don't know what that is. Okay. There is not one. And it gets more complicated. We're not going to worry about that. For most materials, even the rubber eraser, if you only apply a small strain, it will largely, we could still call it elastic. Like even this curve, for a small strain, has an initial slope. Okay, so what's the other assumption that's going on here, telling us that we only need 2 things, E and nu? So it has to be elastic, and it has to be linear elastic, which means, again, that this curve that you measure is a straight line. So that's the first thing. Now there's one more thing. This is really interesting, this next part.
ISO.
Go ahead. What?
Isotropic.
Oh. Look at what he just said. What does that mean? What does it mean to be isotropic? A material to be isotropic?
Just like you push it in from any direction, it responds like this, a response similar.
Exactly. You nailed it, man. So if this is a material, and if we carved out a specimen in this orientation, if we did that, it would give us this response. And if we carved out another specimen in this orientation, it would give us exactly the same response. No matter what orientation we have, it always gives you the same linear P delta response. If the material does that, we say that it's isotropic. And if it's isotropic, it's fully characterized by these two guys here. Okay. What's an example of not isotropic? Well, if I take a specimen of material that is like now a slate. Slate has all kinds of oriented, little tiny at the super small scale, oriented planes in there because of the way it was created. If I squeeze this, let's look at the extreme cases. If I squeeze it this way, oriented perpendicular, I get a certain P delta. If I squeeze it when it's oriented differently, I'll get different stiffnesses depending on the orientation of that microstructure. And so that material is not isotropic. And it turns out this all can be handled by theory of elasticity, and it ends up being handled by adding more fundamental elastic properties. And I'll just mention quickly, because I think this is cool, stress is a tensor, and there's a completely general relationship between stress and strain. And if you actually work out strain, there's like 6 components to it, and stress has 6 components. And if you work out all the possible linear combinations of strains to give you stresses, you end up getting 81 coefficients. And so a completely general material that's a continuum, that's elastic, is fully characterized by 81 properties. But if you do some theoretical thinking, you can end up reducing this to 21 because of things about symmetry and all kinds of other stuff like that. And so if you keep on making assumptions, eventually you get to isotropic and you get down to only 2. And so like this sucker here, that would be something they call transversely isotropic. And I can't remember, it's either 5 or 6 elastic constants for that. So you would have to do tests in different orientations of this to back out these elastic constants. Okay. So look at this. The little world we thought was so simple, E and nu, and we're done, has a huge amount of assumptions, and it only applies to like this perfectly isotropic material. Rock is not really isotropic. Like this is slate. This is not isotropic, okay? However, as a first approximation, it's quite reasonable to assume it is, and then we get a E and a nu. And if we have to assume that, let's call them E nu. I'll call them prime. They're like effective Young's modulus, effective Poisson ratio, meaning if we assumed it was linear elastic isotropic, this is what we would have measured. This is what we could characterize it with. And depending on how complicated you're going to do once you start using this, that might be sufficient. Okay. And so I just got a few more things to say, then we'll stop. For a typical rock, the first level deformability is we assume linear elastic isotropic. If we assume that, we need to get these from laboratory tests, and we get those by either, here's another one, doing this test, or doing this test. Okay. If we do this test, we'll measure a modulus. I'll call it ET. If we do this test, what are we going to get? We'll get a modulus that I'll call EC. So if we do this test, I'll call it E compressive. And if we do this test, I'll call it E tensile. Are they going to be the same? What do you think? If it was linear elastic isotropic theoretical material, would they be the same?
Yeah, I guess, but for real rock, it won't be the same.
You are correct on both points. How will it be different? And let's talk about a granite. Do you think that, so I'll call this EC. EC, is it greater than or is it less than ET? So the compressive stiffness, is that bigger than the tensile or is it less in general for granite? What do you think?
Well, I guess EC is smaller.
You're thinking
no,
smaller.
EC is compressed. Oh, sorry, I make a mistake. I think ET is smaller because
ET is smaller, you think. Why?
Yep. Well, because for the real rock, it can be compressed by a larger force than tension.
Yes. Okay. So
is
here it is.
Is it the
go ahead.
interlocking? Is it the interlocking? Because of interlocking?
You're on the right track. What did I say about the granite? Do you remember when we looked at that stress strain compressive curve? It did this. It did a stiffening. Why was it stiffening?
Because of the crystal rearrangement.
Not for the granite. Nothing rearranged yet. That's for the granular material. I talked to, remember the granite
closure.
Crack closure. The granite has like little cracks in it, and when you squeeze it, they start to close, which means it gets stiffer. So it does this. Okay. Now, think of go back over here, right here. Here's a simple concept of a rock with grains and springs at the interfaces. Okay. Now let's say that, and if this was the system, every single contact has an interface. They're all closed to begin with. If I squeeze this, I'll get a modulus, and if I pull it, I get exactly the same thing. All we're doing is exercising those springs. Be the same thing. Springs don't care. But that's not a rock. A rock, a granite rock, this guy's not there. Okay. Now think about it. If I pull it, I exercise 1, 2, 3, 4, 5, 6, I exercise 8 springs. It has a certain stiffness. If I push it, once it's closed up, these two surfaces start to touch and a spring goes in there. And so it gets stiffer. So if I look at, it's just freaking crazy complicated. This is the granite, it does this. It closes for a while. We don't measure the slope here. We measure the slope in that linear portion. And this is the slope we typically measure. And that's what we call the modulus of the granite from a UCS test. And so that is going to be bigger than the tensile strength because that formed later. The tensile guy didn't have a bunch of guys in there. So when you pull it, there's no new surfaces that are forming. So it has a certain stiffness. But when you squeeze it, after it closes up, it has a higher stiffness. So the result is that a typical for lactobonate granite, the tensile stiffness is modulus is 42 GPa, and the compressive modulus is about 69 GPa. So when you squeeze lactobonded granite, it's stiffer in compression than it is in tension. So right away, even with all these simplifying assumptions for this quite simple intact rock, it's already a little more complicated. It's not just E and nu. The E is going to differ depending on how it's loaded because of that initial microcrack fabric that's in there. And of course, if the granite, you know, has been created in such a way that there's almost no initial microcracks, then these things are almost the same. Okay. This is also a thing that is typically never really thought about in rock mechanics. What people typically just do is they do a UCS test, they monitor stress strain, they never even care what's going on here. They just do this and it breaks, and they sit there and they take the slope and they say that's the modulus and they're done. But actually, if you look at tensile tests on that same thing, you will find that the modulus will be less. Okay? Which means that the material is not behaving, even simple granite is not behaving like a linear elastic isotropic body because its modulus is different depending on how it's loaded. So if you have a general body of rock and it's loaded in some weird way, you know, this region might be in compression, but this, you know, this region might be this, but this region might be in tension. Like if we had an excavation in a bigger system, right? This part is in compression, this part is in tension. So actually this material is stiffer than that material. This is almost never accounted for in any kind of rock conceptualizations. This could be done. You could even, you know, build a continuum model. Well, this is not, it's not obvious what the hell you would do because you would have to build this in because you don't know where the tension's going to be and where the compress. That's based on the loading configuration. So very few constitutive models give you two input parameters. In principle, they should. They should give you two E's, but typically they don't. They just say, give me an E. And then they assume it's linear elastic isotropic behavior. For many, many situations, it doesn't matter. It doesn't make much of a difference. And for many rocks, these ET and EC are quite close, depending on how much initial microcracks are in there. But this, it turns out, I would argue, is a quite important thing for a bonded particle model. And an ideal one should match both. And we can match both because if we put in initial gaps, the model will naturally have a lower tensile modulus than a compressive modulus because it'll be the same microstructural physics and it will be an emergent property that the tensile modulus will be lower than the compressive modulus. Okay. Are people with me?
Yeah.
Okay.
Totally with you.
So deformability, not so simple, but we're going to keep it simple. Typically, to start with, use an E and a nu and assume ET equals EC. So that means typically what we would do is you do a UCS test. That is the test that people always do in rock because it's easy. And if you do a UCS test, you get stress strain. It actually does this. And you go to here and you get the slope, and that's EC. And that's what you use. Okay. And so that's what we're going to do as an initial part of calibrating. We're going to do a UCS test. And just like in the laboratory, they also in the laboratory get Poisson's ratio from the UCS test. Again, they get it in this part of the curve after those things have closed up. And so that's what we're going to do when a first pass model. We're going to say, can we make an isotropic packing of particles And can we choose the stiffnesses of the springs such that we can match the E and the nu that we get from a UCS test? That's going to be a typical starting point of all bonded particle modeling, and that's how we're going to start off with and try to match deformability. Okay?
Okay.
Okay, good. It's past the time, so we're going to stop for now. We're going to continue this lecture next week, and we'll see if we get done. We probably won't, and so we probably will have one more lecture after next week.